I'm going to call it gamma, but gamma is the connector between time, length, and mass, how they appear when they're not moving versus when they are moving. For this first one, if we find gamma for an everyday speed of 30 meters per second, gamma's equation is this great big square root thing. Whenever I find it online, it's always written that way. Because I'm going to do some of the steps in my head, I'm going to rewrite it and put it this way. I can just do a bit of math in my head a little bit easier that way. For the everyday speed of 30 meters per second, let's put in what we know. 1 over the square root of 1 minus 30 over 3. The speed of light is 3 times 10 to the 8. In that line here, I'm going to show lots of work for this first one. In that line, the 3's cancel. So it's really 1 take away in the numerator. The 3 of the 30 cancels, so we're left with just 10. On the denominator, the 3 cancels, so we're left with 1 times 10 to the 8, which is just plain old 10 to the 8. Oops, and up here I forgot to put the square, and we need a square here as well. And that's all under the square root. Taking it one step at a time, the square root of 1 minus, if we have 10 to the 1 divided by 10 to the 8, the exponent rules are subtraction. That makes it 10 to the minus 7, and then we've got to square that. That I can still do in my head is exponent rules. If we're squaring an exponent, we multiply the two exponents, so 10 to the negative 7 squared is 10 to the negative 14. Now, believe it or not, I can still do a bit of work in my head. This is 0. Let me make sure I do this right. I think I have to write 1, 2, 3. If I wrote 3 zeros, that would be 10 to the negative 4. So I need to write 13 zeros to get 10 to the negative 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then the 1. All of that is under a square root sign. Yikes, I can still do one more step in my head. If it was 1 take away 0.1, I'd get 0.9, I'd get 1.9. If it was take away 0.01, I'd get 0.99. Since my 1 is in the 14th place, I'm going to get 14 nines. I think I'm doing that right. All of that under the square root. Now, I can't do the next step in my head, but we can think this through a little bit. Whenever we take the square root of a number between 0 and 1, we always end up with a new number that's a little bit closer to 1. For example, if we took the square root of 0.49, you can play with your calculator, but the square root of 0.49 is 0.7, closer to 1. If we took the square root of 0.64, the square root of that is 0.8. If we took the square root of 0.81, the square root of that is 0.9. If we pick some numbers that I couldn't do in my head, like 0.99, if you took the square root of that, you're going to get a number that's a little bit closer than 1. In this crazy thing, your calculator can't do it, but if you could put that big ugly number in your calculator and then square root it, you're going to get a number even closer to 1. So it's 0.99. I don't know how far it goes. I'm predicting that there's going to be more than 16 nines. Oops. More than 16 nines, which means when we do our division, our answer is going to be 1 point, a whole bunch of zeros. Again, I'm not sure, and my calculator isn't going to help, but I'm thinking we've got at least 15 zeros before we get to a real number. Basically, what this is saying is that the everyday speed of 30 meters per second to roughly 15 decimal places or more, the gamma is 1. It is so close to 1 that we don't see any special relativity effects if you're only going 30 meters per second. If you think about like the Olympics or the stopwatch on your watch, they go to like 2 decimal places. Maybe certain sports or certain events would have 3 decimal places of time. But to get to 15 or more decimal places of time, we don't have any tools that can get that accurate. So basically what this is saying is that for all intents and purposes, special relativity at 30 meters per second doesn't really have an impact. We're not going to notice any time, length, or mass change because that gamma factor is so close to 1.